Hello and welcome to another video here on my channel. My name is Ruben Duarte and I'm a GIS specialist by profession. In today's video I want to show you something interesting. How within a line shapefile, in this case I'll use a railway line as an example, we can automatically identify curves, and not just any curves, but specifically tight curves. This exercise will be carried out entirely in QGIS, so without further ado, let's get started with the video. Alright, so here we have our railway line, and the final idea will be to identify the sharpest curves in our network. Let's start by creating intermediate vertices along our line. To do that, you go to Processing Toolbox and search for Densify by interval, this second tool here. As the input layer, we'll use our train_line. In the interval parameter, we define the distance in meters, since we're working in meters, that we want between each vertex along the line. In this case, I'll choose 10 meters. Then down here, I'll select the location where I want to save the output and click OK. I'll name it train_line_dbi, so train_line followed by the acronym of the tool we just used, dbi, which stands for Densify by interval. Here we can see the line, and we can even open the attribute table with the different vertices. In fact, we can compare one with the other if we add the original layer. Let me just start editing here. We can see that we already have quite a few vertices, the red points, but in this new layer we have even more vertices, all aligned every 10 meters. As you can see, they are much more evenly distributed, spaced at 10 meters intervals along the line. Now we are going to start working with this new layer. The second part of this process is to extract these vertices, so we'll search for the Extract Vertices tool. The input layer will be line_dbi, and we just need to choose where to save the output. I'll give it a similar name to the previous one, but this time adding the new acronym EV, which stands for Extract Vertices, so we always know what the previous step was. Let's run it, and as we can see, we now have a new point shapefile with points distributed every 10 meters along the line. If we open this new attribute table, we can see that we now have several additional fields. However, the distance field will be the important one for us to distinguish the curves along our line. Now let's move on to the next tool. We'll search for points to path, which is located under vector creation. The input layer will be the most recent result we created, the one from Extract Vertices. In the order expression, we'll select the distance field we just looked at. And now we just need to choose where to save the output. I'll follow the same name logic as in the previous steps, click Save, and then click Run. So what does this result show us? It shows us a line with a defined start and end. The line is still structured with the vertices spaced every 10 meters, just as we saw earlier, and we can also confirm that the vertices are still here. What we need to do now is use explode lines to split this line into multiple individual segments of 10 meters each. That way we'll have separate 10 meter segments instead of one continuous line. Here's the tool. As input layer, we'll choose a line _dbe_ptp. Then we select where to save the output and click OK. As we can see, if we open the attribute table, we'll still have our line, but now it's divided into 10 meter segments. In fact, we now have 20,352 new features. I can even make a selection here to show it. We're now able to select the line by individual segments. So now we have our line completely split into individual segments. Let's open the attribute table again, just like we did earlier, and place it down here. What we are going to do next is add a new field. We need to toggle editing, click on add new field, and create a field called direction. The field type can be set to decimal, and then click OK. Here we click on Open Field Calculator, choose Update Existing Field and select the Direction field. Now we're going to use the following expression. Degrees, open parenthesis, azimuth, parenthesis again, start underscore point, then open parenthesis and type geometry, close parenthesis, comma, and underscore point, open parenthesis, geometry, and then close with 3 parentheses. All of these expressions will be available in the video description, so it's easier for you to copy and use them without making any mistakes. After closing all the parentheses correctly, we'll click OK, and this will calculate the direction of each individual segment. So now we have our direction field calculated. Next we'll search for the Add Auto Incremental Field tool. As input layer we'll use our most recent layer, and for the field name I'll use the ID underscore seg, which stands for segment. I want the segments to start at the value 1, and then we just choose where to save the output in our folder and click Run. So now we have our new layer, which is this one here. If we open the attribute table, we can see that we now have a sequential ID. The value 1 corresponds to the first segment. Let me show you. If I open the attribute table again, we can confirm that the first visible feature is indeed segment number 1, this one is 2, this is 3, 4, and so on. At the very end of the line, we'll find the last segment in the sequence. So what we need to do next? We need to add 2 new fields to this table. Let's click Toggle Editing and then Add New Field. I'll create one field called y plus 25, set as an integer, and another one called y minus 25, also as an integer. I'll organize the columns so that these new fields appear before ID underscore segment. What I'm going to do is compare the 25 segments before and the 25 segments after a given segment. For example, imagine this segment here. I select just one feature, then I'll consider the 25 segments before it and the 25 segments after it and calculate the curvature. Specifically, the curve radius in meters, considering all those segments together. That means 25 segments forward and 25 segments backward, which corresponds to an analysis of over 500 meters in total, since each segment is 10 meters long. 50 segments multiplied by 10 meters equals 500 meters. And that's the main idea behind this video. Let's go back to the processing toolbox and search for join by field value. This one here. As input layer, we'll choose our most recent version of the layer. In the table field, I'll select y plus 25. We can start with this one. For table number 2, we'll use the same layer, and the field will match it with ID underscore segment. In the list fields to retrieve, we'll select direction and then click OK. For the join prefix, since we're working with the plus 25 field, I'll name it p25 underscore. And finally, I'll choose the location where I want to save the result. I will name it join underscore p25, for example. Click Save, and then click OK. 20,352 features from the input layer could not be matched. So we get an error here. Let's try to understand what's causing it. Okay, we can see that the ID underscore segment is set as real and not as integer. That means that when we did the calculation earlier, the join couldn't match the values correctly. So what I'm going to do is create a new ID segment field again. I'll click on calculate field, update existing field, and on ID segment, I'll set this new field to be equal to id underscore seg. I click OK, and now I can delete the original field because we no longer need it. Let me organize the columns. Click OK. But now we have the same values, we still have the same ID segment values as before. However, in the new field, the one with an extra caret in the name, the values are now stored as an integer type. So the numeric values remain the same, but this time they are correctly defined as an integer, which allows the join operation to work properly. I also noticed something else that we need to do to avoid errors. Before performing the join, we must make sure that the y-25 and the y plus 25 fields are properly filled. In other words, we can only run the join after these two fields have been calculated and contain valid values. So let's start by filling in these two fields first, and only after that proceed with the join operation. Let's start with the I plus 25 field. We'll choose update the existing field, then go to fields and values and calculate it as id underscore segment plus 25. And then for the y minus 25, we'll do exactly the same thing, but instead of adding 25, we subtract 25. So id segments minus 25. Like this, and click OK. Now we have all the values properly filled in, and we can proceed with the join. Let's search for join attribute by field value. In table field, we'll select the y plus 25 and match it with id underscore segment in table 2. The field we want to retrieve is direction, which will be our target field. For the join field prefix, we'll use p25 underscore and we'll save the output as join underscore p25. Then we click save and run. This time it worked correctly. We do get a warning saying that 25 features were not matched. This is expected since we're adding 25 to the segment ID. The last 25 segments don't have 25 segments ahead of them. They're already at the end of the line, so there are no following segments to analyze. Now let's move on to y minus 25. We'll search again for join attribute by field value. This time in the table field we'll select y minus 25. In table 2 we'll choose id underscore segment again, and then select direction as the field we want to retrieve. For the prefix, instead of p25 we'll use m25 representing minus 25. As the output name we'll use curves, since this will be our final result. In other words, this will be the final table. We'll define a few more fields and perform some additional calculations, but this will be our main output layer. Now we click run, and as expected we see that 25 features were not matched once again. In this table we are going to create a new field. Let's click toggle editing and then add new field. We'll name this field curve center and click OK. Next, we will calculate this curve center field using the field calculator tool. So we choose update existing field, select curve center, and once again enter an expression, which will also be available in the description, just like the previous ones I mentioned. To move forward, I'll skip this part of the video. The full formula will be in the description and it's also displayed here on the screen in larger format. Finally, we'll create one more field. We'll call it radius underscore center and click OK. And now we need to enter another formula. This one is much simpler than the previous one. We select update existing field, choose radius center, and use the following expression. 500, and then we divide, type radians, open parentheses, go to fields and values and select curve underscore center, close parentheses, and click OK. Remember that the value 500 represents the total length of the segments being analyzed, 25 segments forward and 25 backward, each 10 meters long, which totals 500 meters. Now let's click on select features, and in radius underscore center right at the bottom, I want to select values below 200. As you can see, no features are selected. That's because we don't have any values below 200, but let's try 600 instead. I'll run select features again. It's not very clear visually, so let me just change the line color to red. Click OK. And now we can already see some highlighted sections, and as you can see, they correspond exactly to curves. The lower this value is, the tighter the curve is. And yes, this is exactly the result we were aiming for. This can be important for several applications. For example, I'm currently preparing a video about railway accident risk analysis, and this type of analysis will definitely be useful there. Let's test another value. The higher the threshold, the more curves we'll be able to select, but we also start including curves that are less sharp and therefore potentially less critical. Let's try 2000, for example. Now we can see even more curves being selected. If we test something like 10,000, almost everything gets selected, and only the straight segments remain unselected. So in this video, the goal was really to reach this type of result. I think it's something interesting. I'm not sure how useful it will be for everyone, but for something like railway accident risk analysis, which is a future video I'm preparing, this is definitely very valuable. Thank you for watching. If you like this video, don't forget to like, subscribe and comment what you want to learn next.